Good. I think we are ready to start. Good afternoon, everyone. Good morning, everyone from different time zones. And welcome to our webinar, Quantum Computing for Optimization Meets Flexibility. I'm Joanna Folbert from Kipu Quantum, and I will be your moderator for today's session. Today's webinar is a unique collaboration between Kipu Quantum and IBM Quantum, presenting how powerful quantum algorithms and flexible hardware access can work hand in hand. I have two extending person with me today. We have two talks. First, we will hear from Jan Trautmann, Head of Development at Kipu Quantum, who will introduce the Iskay Quantum Optimizer, a newly released Qiskit function designed to solve complex, dense optimization problems using one of Kipu's flagship algorithms, BSFieldDCQ. Then we will be joined by a group product manager at IBM Quantum, Andrei Constantinescu, who will walk us through the Flex Plan, IBM latest access model for their quantum hardware. To get us started, I will suggest Jan, Andrei, you can introduce yourself and talk a little bit more about your function at Kipu Quantum and IBM, and then let us start with presentation about Qiskit function Iskay Quantum Optimizer.
Yeah, sure. Maybe I just start. So hey, I'm Jan. Happy to speak today about our Iskay Quantum Optimizer. I actually have a background in physics. I was starting a lot with quantum computing. Actually, I was starting to build quantum hardware back in my days, and then I started to move to software. And I'm one of the responsible peoples in Kipu to create our algorithms into software products. And one of them I will present you today with our Iskay Quantum Optimizer.
Right, thank you, and Andrei, the stage is yours.
Hey, thank you for inviting me, and really happy to be here with all of you. Yeah, my name is Andrei. I lead the product access group at IBM Quantum. My background is in engineering and software. I spent different positions within IBM, and I joined Quantum 3.5 years ago. And my focus is to build the IBM Quantum platform and provide a seamless experience from an access perspective, but also tools that users will need to run algorithms, scheduling jobs, analytics, everything end-to-end. That means platform access and platform experience.
Great, thank you so much. Let us share your screen, Jan. I'll just... For everyone, feel free to drop your question and chat at any time. We will cover as many as we can in between, maybe in between two talks and at the end in our Q&A session. So please put your questions and discussion. Thank you so much.
Yes, let's get started with our Iskay Quantum Optimizer. Before we dive a little bit deeper into the topic, I would like to give you a brief overview of what Kipu actually is and what we are doing. So we are a German-based software startup specialized in designing quantum algorithms that are running on current quantum computers. So devices like IBM has, and where we can start to tackle real industry problems. And our mission is to make quantum computers useful as soon as possible without having to wait for fault-tolerant quantum computers. We also believe that we already are reaching an inflection point where quantum computers can be useful, like the devices from IBM, by using our technology to narrow down or to shrink down circuits that we can run really large problems on the systems. And we believe that we reached the crossroad where we see for narrow applications, our algorithms on quantum hardware are on par or even outperforming in terms of speed, accuracy, or energy consumption classical solvers. How are we actually doing this? So what we are doing is we create hardware-specific and application-specific quantum algorithms. And in this kind of way, we are trying to squeeze as much as possible out of the current quantum hardware. So one of the biggest bottlenecks is that if you would like to solve real industry problems on current quantum computers, the circuit depth is often much too long, which means that you require too many gates to solve even small systems within the coherence time. So you run your execution. At the end, your execution time is longer than the coherence time, which means you cannot measure anything useful anymore from the quantum devices. We are actually tackling that problem by first making our algorithms application specific. In this step, we also add counter-diabatic protocols into the system, which are resulting in this massive compression that we have shown you here on the slide. We have seen, for example, that we are able to reduce typically a circuit depth of 10 to hundreds. So this allows us to even solve problems using the 156 qubits of the IBM processors, and that we can really run state-of-the-art problems with that. And on top of that, we also have what we won't talk about today. We're making our algorithms even more hardware specific by applying our digital analog technology. This is something that we are currently more developing the research state, but our DCTO compression, we are productizing. This you can already use in our newest algorithm that we also have published already. So let's go back. So one of our flagship algorithms is actually the bias field DCTO algorithm. This is an algorithm that combines our application specificity by looking at optimization problems and uses these counter-diabatic protocols. For this algorithm, we start actually from the problem formulation. This could be a highly connected, higher order constrained binary optimization problem, or like, for example, a job shop scheduling problem. We feed this problem into our algorithm, and from this we create a quantum circuit. And this quantum circuit is then based on our counter-diabatic protocols that creates this massively compressed circuit that we then are running on the quantum hardware. We execute it on the hardware and take back the result. And this result we are feeding again into our algorithm in this kind of way that we are solving the optimization problem. We get an approximate solution somewhere in the solution space of some energy and of lower energy. And then in the next iteration, we initialize our iteration close to this found solution state, that we are not exploring the full Hilbert space anymore, but starting from already previously found solution. And this is what you can see on the right side here in the video. So we start from a very high cost, and then with every iteration, we are pushing it further down. What we also would like to emphasize here, that this is a non-variational approach. So we do not require to add in here a classical optimizer around that. This is fully everything running on quantum, and we just do it iteratively. What's also interesting here is that we are only using a local search at the end, at the final point of algorithm, to do some kind of error mitigation, because in this algorithm, there is no error mitigation at all integrated, and we can already heavily outperform other quantum algorithms. And also the costs are pretty low, because we only require 5, 10, or 15 iterations, but not 100 or 200 if you, for example, would like to run QRUA. For sure, we also benchmarked our algorithms on actual quantum hardware. So here in this case, we took a higher order binary optimization problem. These higher order problems are occurring in many applications, like, for example, protein folding, or also when you are using time windows and scheduling problems. Then you obtain higher order problems, which means that the variables are you have dependency on variables in polynomial order. So this could be 3 or order 4 or something. These problems are actually super hard to tackle on classical solvers because they typically have to map it back to linear or to quadratic system to solve them, which then requires a massive overhead. So they are non-native to what classical systems can do, and also not native to what D-Wave is doing. And therefore, we think these problems are actually highly relevant and are the first cases where there's a high potential of approaching the quantum advantage level or even outperforming classical solvers, as we have shown here for a narrow application. So we ran here. So what we did is we fixed the time to execute our algorithms and also the classical ones. And then we were comparing the accuracy of the answers. And as you can see here, actually by running our bias-fitly secure algorithm, we reached accuracy pretty close to the ideal answer, and it was even able to slightly outperform simulated annealing and tabu search. The next best quantum algorithm was then the D-Wave system, where we used the internal library of D-Wave to map the Hubo problem to Cubo and then executing it there. This reached also still pretty good result, but could not compete against our algorithm. And for sure, we also compared it against another quantum benchmark on digital hardware, which was in this sense a variational algorithm, but this one heavily failed because the resource demand was too crazy in this sense. To make our solutions also more easily accessible, we joined our forces with IBM and then published our bias-fitly secure inside our Iskay Quantum Optimizer as a Qiskit function. And the goal behind this is to make our technology as easy and as ready-to-use optimization solution. What does this mean in reality? So for the Iskay Quantum Optimizer, the only requirement that you have to provide is an objective function. So you have to convert your optimization problem into an objective function, and then you submit it via an API call to our Qiskit function. From this, we actually are creating then a quantum formulation, so you don't even have to care about quantum. It's fully fine when you know a little bit of math and when you know how to formulate your problem. We are adding our counter-algebraic terms. We are creating the circuit and we execute it on the quantum hardware, and we also do the post-processing. And then what we return is the solution. And this what we have shown here, it's, for example, the solution of a max cut problem, where we then return you the bit string with the energy and the solution. The nice thing is that this automatically uses our compressing technology from our bias-fitly secure algorithm. It's actually easy to use to solve optimization problems, and it can be used from various workflows because it's just an API call to the Qiskit function. And what we also have in there is a one-to-one mapping between classical variables and the qubits. So if you have, for example, 156 qubit problem, we can run this on the largest IBM devices and fully execute that. And the nice thing is also it's fully automated workflow. So we handle the quantum formulation, we handle the hardware iterations, and we also handle the post-processing. And you do not have to take care of that, making it easy to use. For sure, we also took a benchmark against existing other optimization solvers on Qiskit function, where we here, for example, are comparing the runtime usage. Runtime usage here specifies to the QPU usage. And because our algorithm is non-variational, we actually require we are four times more efficient than the other providers. And because we also have the workload of solving this optimization problem on the quantum device and not on the classical side, we also can use a lot less classical CPU power, resulting in a total reduction time of time to solution, where we are 2 times more efficient. What's for us also very important is that we made the benchmarking problems that we are showing on the documentation of Qiskit function publicly available. So they are available on GitHub. You can download them, you can tackle them also with classical solvers, and you can make your own performance benchmark. With this optimization solver, we actually can address a huge amount of optimization problems from various fields and with various use cases. For example, one of the classical things is optimizing delivery routes, where we then can cut down fuel costs, or also by optimizing the assignment of fuel-saving flight carrier on aircrafts to flights, we can also reduce the environmental impact of your traveling routes. You can also use this, for example, for more efficient resource allocation or complex scheduling, or also what we have done to analyze the grid stability and also then to optimize your grids, which is heavily interesting for example, communication networks, also for your energy grids. We are offering our our system in three different trial or tiers. The first thing where we are happy to use is the free trial. So everybody is welcome to sign up. And then we're offering a 2 weeks free trial period without any costs, where you then, for example, can play around. You can use our benchmarking problems that we made accessible. You can tackle them with our optimizer. You can also tackle them with your own algorithms, and you could compare the results with that. We are also offering, if you are then convinced by the functionality, we are offering a monthly subscription. So if you are an expert in optimization, and you would just like to run it on quantum hardware, you can then go to our monthly subscription. This means unlimited access to the algorithm. We are also, in addition to that, are offering then one-to-one expert sessions to support in terms of mapping. This is all then done under standard license agreement. And if you would like to dive a little bit deeper, like, for example, you work in industry and you would also like to have support going from the business problem to actually optimization problem and looking at the size, what you can actually tackle on hardware, what does this mean for your business, which use cases we could tackle, then we are also offering to do a joint project where we then are offering to tailor our algorithm, having a focus actually on tailoring the algorithm to the IBM hardware, and then also go deep with you into your individual problems. This is, for example, the model that we did with several industry partners, like, for example, BASF, MasMovil, Vinci Energies, also Moewe. And we are really happy if you would like to explore our Iskay Quantum Optimizer. Please feel free to contact our sales team, Eugene and Robert. And here also we have the QR code. And I'm really happy to receive any questions you have.
Yeah, we have some. First, Jan, you can take the chat. Does any QUBO solvable using BS-field DCQ approach? So does any QUBO problem is solvable using BS-field DCQ approach, I assume? That's
yes,
the question.
So this depends a bit on what you mean with any QUBO problem. For sure, we have the hardware the hardware constraints, like, for example, only 156 qubits. And then we have to check how fast we can go, for example, to an all-to-all connected problem, because as you probably know, the IBM hardware is pretty good. But if you have 156 all-to-all connected problem, it maybe also reach its limits. But this is something we would be really happy to explore. So our Iskay optimizer, in terms of what can it take, is really designed that it can take any cost function, QUBO or QUBO, and that we then solving it together.
Great, thank you, Jan. Have we benchmarked our solvers against other machines on QUBO?
Our solver here is mostly only benchmarked against the IBM devices. For sure, we also took QUBO problems into the system. They are also published there. But we didn't benchmark this, for example, against the IonQ devices, because we were running problems of 156 qubits, which is currently not possible on other hardware.
Okay, thank you so much, Robert. Thank you for sending the GitHub link. Another question: I have been exploring the circuit optimizer that Classic has. Any comment on this?
So Classic, I think, works in a little bit different regime. Classic works that you provide a circuit and then they optimize the circuit for you. What we are doing is we do not take the circuit, we start really from the problem and are then putting our technology, well, we create a completely new circuit that is then running on hardware. So we didn't benchmark our algorithm now against Classic, but we follow a different approach. Generally speaking, we could also play, or we could add the tricks of improved compiling to our circuits, but we didn't add that yet. Similar like error mitigation. This is also not done yet in the system, and still we are reaching pretty good results. So this could be also something that we could explore together in a joint project, adding these both technologies to further enhance and improve.
Next question: are there any performance comparisons between this optimizer and others, such as Corba?
I do not know this optimizer yet, but as I said, what we offer is we actually ran it on the hardware, and then we were reporting the hardware results, and also the hardware runtimes. And for sure, if we have this optimizer at hand, we are really welcome you to just take the examples that we have, pushing it on the optimizer and then compare. We would be happy to do this comparison with you.
Okay. Details about the cost of monthly subscription, I think this could be taken by Robert. I think maybe, Robert, you could answer or contact this person. More questions, several questions. I want to ask you, please, if you compare it with quantum variational imaginary time evolution from IonQ, Nick.
Can you repeat that question, please?
I want to ask you, please, if you compare it with quantum variational imaginary time evolution from, I think someone means here IonQ, right? That's the question from.
But we didn't run the same problems. I mean, for this, we would have to need access to the solver or to this algorithm, and then we have to run it on probably the same devices. Like if it's from IonQ, we would have to run it on IonQ device to actually have an honest benchmark. Because as I said, the problem is we were testing with 156 qubits, which is currently too much for the IonQ hardware. But what I just from looking at the name, I don't know how it deep down works. Because it's a variational algorithm, I would assume that we are able to actually, I would guess that we are able to have the same performance, but will require less iterations because it's a non-variational algorithm.
Yes, and the last now, and I think now we can switch, after that we can switch to Andre. A clarification to my question. So previous question, have you seen similar improvements for Kubo problems against D-Wave or simulated annealing?
Okay, that's actually a very interesting question. So we are able to perform on pair, for example, with Kubos, simulated annealing, or on D-Wave, in terms of that you can reach the same fidelity. But for sure, if you would like to say, okay, simulated annealing is pretty good for Kubo problems, then you can solve much larger systems and also probably faster. That's the reason why we say for quantum, it's not that interesting to only look at Kubos, but to look at Hubos, because we do not expect that we have a massive advantage here against D-Wave, which is native Kubo, or also simulated annealing. So there we would have to take a look into really specific problems where these systems are not that good in solving. But on the general side, we would expect that they probably reach a solution faster. That's why we are looking actually at Hubo problems where these systems are really pushed to their limits.
Thank you so much. I would like to switch right now to Andre, and then once again come back to other questions and Q&A session. Andre, please explain us, how does the new IBM FlexPlan work?
Yeah, thank you. Thanks, Jan, for the presentation. The function looks really interesting. Let me talk about two things, and I'm going to split this presentation into things. One, the new platform, because we're in a migration process from the existing IBM Quantum platform to the new IBM Quantum platform, and FlexPlan and access is available only on the new Quantum platform. So you probably have seen recently a lot of announcements from IBM, and this is following that direction, right? Quantum for us has to be performant and has to be easy to use. And performant and easy to use implies a platform that comes with specific enhanced security, compliance, seamless integration, and several other capabilities that existing platform is lacking. Migration is never easy. I think if all of us been through something like that before, it's always challenging, especially in the new technology. But this is a necessary migration for us to support the scale that we have announced, and also supports the utility scale experiment and upcoming advantage scale experiments. So this is a critical step. And this platform brings far more capabilities than we have today. If you're an academic, if you're an enterprise institution that wants to operate at scale, wants to have utmost security, wants to run production workloads, the new platform will be ready for that. Also, one thing that we missed on the existing platform is addressing different regions out of the box. So we're in Germany, existing platform doesn't have, for example, German language. So things like this are nice to have out of the box that makes the users to onboard faster, this platform, and also the documentation and the whole user experience. So look and feel will be the same if you're part of the open plan on existing platform, or if you're part of our premium plan or any other plan. Everything will look more or less the same, with a few changes that will enhance security and accessibility on this platform. So sunset is July 1st, end of this month. This is the old link, and the new link will be at quantum.cloudibm.com. Keep that in mind. If you're an open plan user today, 1st of July, this existing platform will be shut down, and I think all of you have been informed if you ever have an account with IBM Quantum. Okay, let's go to it. What is Flex? Flex is a new access model, and this is basically the I'll say the punch of it, right? You can get access for 1 year for 30K minimum entry point to all our fleet. And comparing with other plans that we have, and I'll show that in comparison, this is a tailored access specific for project-based access, right? Either you want to test a function like Jan just showcase, or you want to run a research, or you want to apply for a grant. We have a project with a specific deadline, right? You're not ready to commit for a long-term year contract. You don't have a very large budget. Flex is where you start. It's 30K, it accesses all our devices, all our regions, and brings a flexible usage. And I'll explain that what it is. But again, you get access to 1 year, all our functions, all our capabilities on the platform. We're Flex on our access plan. So we have open plan, 10 minutes for free per user every month. Flex is 1 year. It comes at $72 per QPU time, but the minimum entry is 30K. We have premium plan. It's $48 per QPU time, but the minimum entry is 250K. And then we have dedicated services, right? So that's when you want an on-prem service, and that's where you contact our sales. Flex, we call it cloud consumption, right? Until now, if you operate on quantum computers, you either have to reach a 20-day rolling window, or you have to reserve specific capacity. Flex operates like a cloud consumption model. You have a bucket of minutes. Let's say you have 6 hours for 1 year. You can come in and consume all those 6 hours within a large experiment, or you can spread them across the year, or you come and show and consume within peaks. Usually the research we discovered the last years operates within peaks, right? I run something in the beginning, very small to understand. I iterate, and then I come and run the large experiment, and I come back again, iterate, run again. So those peaks, today there's some constraints if you use different type of access modes, but with Flex, basically we take that barrier away, and you get that flexibility depending on the type of execution mode you want to run. It's a batch, job, or session. You can achieve those peaks and run your research into it. So it's very simple to use. If you use any other cloud service at this point, it operates exactly like that. You don't need to calculate your amount of minutes. Everything is within analytics. I will show that in a short demo. You don't need to refer at the past usage, as it's a 20-day rolling window. Is the minutes that you have are the minutes that you can use, and you just have to estimate the amount of minutes that you will need for your specific experiment. So let me show you what is Flex and how it looks like. And again, this is the platform, right? Today is early access, but again, 1st of July, it will be the default platform. When you're signing in, you select the region that you want to operate in. I'm in Europe, and I want my data, let's say, to stay in Europe. I select Frankfurt region, and I log in with my IBM ID. This platform has SSO functions out of the box. So if you're a large institution or an academic institution and you want to connect to that, it's a very simple click access. This takes a while. Okay, so I'm in the platform and I have access to Flex. What I will do is go and create an instance. I have Flex, the minimum capacity, which is 6 hours, 20 minutes. It's around 400 minutes. I have several instances that I opened here before. And let's say I purchase Flex. I have the capacity. What do I do now? Well, you'll create an instance. You can call it, right, Kipu. You select the region we selected in the beginning. You select Flex. You will see other plans here. I have access to other plans. You'll probably just see standard and open and Flex. I set a limit. Let's say I want to allocate 100 minutes. I set this limit. This instance, if I click this box here, this instance will consume only 100 minutes. So you can split your minutes in allocation to different instances and decide for what projects you want to use. If I don't select this limit, if I have 6 hours, I consume the 100 minutes allocated to this instance, it will continue to consume from the 6 hours. So it will not stop your project or iterations. Set the limit. Next, I can add all the systems, or I can pick up a specific system that I want. Those systems are all in Europe, are in Enningen in Germany, our IBM Quantum data center in Europe. We have 3 systems, Aachen, Brussels, Strasbourg. Aachen 156 qubits is one of the most performant systems across our global fleet. I can add all the systems to this instance by default, or I can tailor and says, I just want Aachen, right? Next, I can add collaborators. You can always edit this, right? And you create an instance, and it should take just a minute. So I have my instance. It is. I see devices. Again, you can always edit this, add the other devices. Oh, sorry. You can see the amount of minutes that you allocated, how many you have left in terms of how many you consume, your CRN, the region that you're in. And of course, the moment you run things, because this is a new instance, I don't have everything. I don't have anything available here, but you'll basically see your consumption real time when you run a job using this instance. And that's it, right? So basically, to just run the instance, you just get the API key, you have the CRN, and you're all set up to run. So it's as simple as that, and we try to make it as simple as possible and as research-oriented as possible. You can also, if you have different regions, and again, you can split your allocations between different regions. You can always bounce between European region and the US region. But upfront, you'll kind of have to split your minutes between those 2 regions, right? Right now, this is a bug and a feature. Some clients or some users, they want that. Make sure that IP does not leave a specific region. That's one thing to keep in mind. And that's it. That is the demo. I hope you find it as simple and as intuitive as possible. If you have any feedback or anything you like to share, I'm all ears.
Yeah, we have one question. Can Flex be flexible enough for 10K, 15K with options to renew?
No, the minimum entries is 30K because we realized that 400 minutes is a minimum capacity you will need to run something useful. We do have other programs that I encourage to contact myself or IBM Quantum team to get specific access for research, but the minimum access is 30K. We also have the PayGo plan, but a bit different than Flex. And of course, with Flex, yes, you can always renew at any time, right? So if you run your 400 minutes, let's say month 2, you can always renew. There's no limit there.
Great, thank you. Do we have any other question on new Flex plan to Andre? No, we have question to DCQO. So once again, Jan, any study materials like published paper or blogs regarding DCQO? It would be helpful if you share this, if possible. Thank you.
For sure.
Yes.
So the easiest thing that I would like to point to there is actually to our website with the Knowledge Hub in there. There we have a summary of our papers and also blog posts. Excellent. And this is not only about our not only about, we also have white papers in there, we also link our webinars in there. And it's not only about our DCGO algorithm, but also broader what we do, for example, in terms of machine learning.
We have another question to you, Jan. Are you able to add constraints to the problem?
Currently, we are not able to add constraints. So the constraints have to be added inside the cost function. So we are taking cost functions for unconstrained problems, Hubo and Kubo. So if we have problems, you would have to add them as, for example, slack variables, or also additional terms into the Hamiltonian that are then, representing these constraints. For example, we are exploring this currently for the multi-knapsack problem. So there are methods to do that. It's just yet not published what we did there.
Great, thank you. Are there any other questions? I'm checking right now. I think we covered all questions right now. Andre, I have one question. Sorry. So Qiskit function were previously accessible only for premium network, IBM premium network. Do I understand it correctly? So with the Flex plan, all new user or every user who is willing to use the Flex option can access Qiskit function. Is it correct?
That is correct. So
okay.
we lower the entry barrier for every user to access the premium features on IBM Quantum platform. So you don't need to be right now part of a quantum network or be part of the premium plan that comes with a larger commitment up front. You can start with as minimum as 30K.
Okay. I think all questions regarding pricing, I encourage you to use the QR code you see right now on the screen, and you will be directly contacted with Eugene or Robert, who can provide you also answers on pricing. Of course, also a pricing question on a Flex plan, which Andre presented, and as Jan mentioned in his presentation, you can use the free trial to check how our Qiskit function is working, and that's for sure very interesting for all who ask it for the how much our function or how much the subscription costs. In your model, would it be possible to incorporate constraint through initial state preparation, Jan?
So no, because in principle in our algorithm it's possible, but not in the Qiskit function, because in the Qiskit function, we do not give access the user to the initial state preparation. In principle, it's possible to include this technique, but not in the Qiskit function.
Thank you. Great. I think we covered all questions. Jan, do you have any question to Andre, if we have already our colleague from IBM Quantum?
No, I think it's everything's fine, because we already chatted last week in London at the event. So therefore, yeah, I think we are settled.
Great. For everyone who asked, everyone who participates today will receive a link to the recording of this meeting, and of course, contacts to Andre and Jan and me to forward us another question. If you have any questions, any requests, use this mail, use our contacts, use a contact of Eugene and Robert and Ray, use the QR code, and I hope you enjoyed this webinar. Thank you so much. And I'm closing right now this session. Thank you so much. See you next time.
Thank you.
Bye.
Thank you.